continue with all. Okay, I got people popping in. Okay, so here's the deal. Today what we're going to do is we are going to continue what we did last time. So what I wanted to show you was, if you go to, I'm going to share the screen so you can see it. First of all, if everybody can hear me, I'm assuming, because I hear people talking to me back and forth. But if I ever drop out or you can't hear me clearly, just I'm going to be monitoring the chat, so you should be able to comment in there, or you can just say something. So here's where we are. Hopefully I'll see our Schoology page. I created a folder for today. So basically what I'm going to do is the following. I'm just going to kind of keep building off of what we did last time. So what we did last time was we were talking about two sample proportion sampling distributions. So I know there's a little bit of a struggle. Someone else coming in. I know there's a little struggle towards the end to kind of get your head around it. So what I wanted to do is just kind of walk through one more example of it so that we can take a look at it. Class ends at 12:15, so I'm going to hopefully be done before then, fingers crossed. But here is the deal. So again, if you want to know the files I'm using, they're in this virtual day folder. Inside the virtual day folder are going to be a couple things. There's an example, then there's a practice that you can work on your own along with the key. I'm gonna put the video up at the end of the day, so it's in another folder. I'm just going to move it over to this folder. So what I wanted to do is I just kind of wanted to talk about what we had dealt with before, so everybody can see that on the screen, right? Everybody can see my notepad and everything. Making sure.
Yes.
Cool. Thank you.
Yeah.
Perfect. Okay. So this is what we did last week when we were doing the thing with the Reese's Pieces. We did this thing called the sampling distribution for one sample proportion. So basically what we were doing is we were trying to come up with this sampling distribution of what's called p hat. So what I had said was, we don't know the real proportion of something. So what we have to do is we take samples of the same size. And every time we do that, we get this little p hat. And what it was how big my sample size was and my number of successes X. And what happened was we ended up with all of these p hats. And eventually, if we started plotting all these p hats kind of on a number line, they started to form a pattern. That's what they did. And what we talked about last week was, like every distribution we deal with in this class, we deal with center, spread, and shape. And our goal is always to try and come up with something being normal. Because if something can be normally distributed, we can answer a lot of questions really easily using normal CDF, using table A, things like that. So what we talked about last time was how we check those. So I'm going to go over real quickly on how we check, and please, ask in the chat if you have any questions as we do this. So the three ways we describe a distribution are the center, spread, and shape. Well, when we deal with sampling distributions, in order to use those words, we have to do some sort of check of the process we're using. So what we had talked about with center is how we determine if something is biased or not. So again, that was our bullseye talk, where we had a bullseye chart, and no bias means we're hitting the target in the middle. The way that we handle that is we handle that by determining if things were done randomly. And the way we'll learn that is if it says it in the problem. If it says things were randomly selected, if it says people were randomly assigned, that's kind of our check to determine whether something meets the criteria for center, if it's an unbiased estimator. And if we do that, we actually can determine the center, and the center will be, what ends up happening is the average of all those samples is going to give us the real answer. Now, again, this formula is on your formula sheet, so you don't need to memorize it. You just need to know where it is. So formula sheet is up front. It's one page front and back. It's on the back side of the front page. This tells me what my mean is, my center. So that's my first check. So any questions on the center check? Okay, if anything comes up, feel free to ask. The next check is spread. So spread is also variability. So this is where my standard deviation is going to come into play. And that check is that new one. Was that a hand or was that? I'm trying to see. Okay. So what I'm going to say is when I look at that, that is where this new thing that came into play. What I told you was I wanted you to use this idea of something called a 10N check. And what I mean by 10N check is this. I want you to look at the sample size, little n. I want you to multiply it by 10. I want you to compare it to what the population is in a problem. And what we need to do is we need to make sure we don't exceed that threshold. We don't go above that 10N. Because if we do, then we violate independence. So our goal is we're given a sample size in the problem, we multiply it times 10. That then will tell us whether or not we violate independence. If we're good on independence, we can now use this formula down here. Again, on your formula sheet, this tells me my standard deviation. So these two give me my mean and my standard deviation. They both give me my mean and my standard deviation. So, okay. Now, the last thing we do is shape. And really what we're trying to do is we're trying to prove that something is approximately normal. That's the deal. These distributions are roughly symmetric when you look at them, these sampling distributions. But we really need to say that they're approximately normal, because if they're approximately normal, we can answer a whole lot more questions in depth. And the way we do that is we need to confirm that in the process of us selecting our sample, we select a large enough sample to give us 10 or more successes and 10 or more failures. So what we need to do is we need to check and see, like when we did this. Yeah, B, what's up?
So for the spread, you have a little thing that says as like the N being the population, right?
This sample,
Okay.
this will be sample.
Oh, okay.
So what it says is the bigger my sample, the less variability I'm going to have. So here's the way, let me give you an example of the way to think about it. We're trying to figure out the average grade in class. If I were to just ask you for your average in class, do you think that's going to have a really good idea of what the overall class average is? Just you?
No.
Probably not. But what if I asked like 10 of you and averaged the 10 of you? Do you think that would get closer to what the real average was?
Yeah.
That's what this idea means. This idea says is as I increase my sample size, all of a sudden I get less variability. So in other words, what happens visually, again, I've drawn this on the board a few times. If I only talk to like 2 people out of the class, I'm going to end up with a curve that's going to look like that. It's going to have a lot of variability. It's going to be short and fat. But if all of a sudden, so this guy is if I were to talk to 2. Now let's say I talk to 10. This is what it would look like if I talk to 10. They're both going to be centered at what that real answer is. It's just the 10 is going to have less variability to it. Yeah, and it is kind of the law of large numbers. What happens is the more we do things, the closer we get to the real answer. The larger we get that sample size, the closer we're going to get to the real answer. So, and again, this is that tipping point thing, because I just talked about independence. We couldn't make it too big, but we have to make it big enough to meet another criteria. So like our shape and our spread, kind of like a push and pull. I got to make it big enough to determine shape, but not so big that I can't determine standard deviation. That's kind of like the push and pull in doing a sampling distribution. Now, in the real world, I'll be honest with you, we're very rarely, if ever, going to be challenged by independence. We're just not. I'm just telling you, we're not going to be challenged by independence because we're talking populations of tens or hundreds or millions, like tens of hundreds, thousands, millions, tens of millions. We're taking samples of size like 250. So really, that's not going to really impact our independence. We do need to worry about the shape. So this is what we talk about with the Reese's Pieces. And if we do all of this stuff I talked about, 10 or more successes, 10 or more failures, big and not too big a sample size, and doing it randomly, we all of a sudden have a sampling distribution that kind of fits this mold down here. Normally distributed, centered at the real answer, whatever the true proportion is, with a calculable standard deviation. So that's what we did with the Reese's Pieces. So I'll pause for a second. Any questions on that? Okay. Okay, here's the difference when we do two sample. When we do two sample, we have to do all of this twice. We're going to have two different samples. We're going to do these checks twice. We're going to check the randomness for the first sample. We're going to check the independence. We're going to check the shape of the first one. We're going to do it for the second one as well. So we're going to repeat this process twice. And what's going to happen is once we do that, we can now call back on some of the rules we had from before. So for example, one of the rules we had from before is if I told you that the sample for males, let's say the mean for males, and I'm just making up a number, doesn't even worry about context, is 11.2. And I told you that the mean for women was 12.8. And I wanted to figure out what the mean of men minus women is. What are we allowed to do in order to calculate that? Like if I wanted to figure this out, how would I do it? This was from before break, the test we took before break. I'm talking means. I want you to give me the difference between two means. How would I figure it out? Yeah, but just subtracting them. Exactly, Naomi. I would just do the mean of men minus the mean of women. I would do 11.2 minus 12.8. I would get negative 1.6. That's what we're going to do with proportions. Is what's going to happen is we're going to have a proportion of men. We're going to have a proportion of women. We're going to find out that the proportion of men is 60%. We're going to find that the proportion for women is 58%. And I'm going to say, hey, what's the difference between men and women? And we're going to do the same thing. We're going to just subtract them. Okay. But do you remember when we dealt with standard deviation, we had to have a different rule. When we dealt with standard deviation, our rules changed a little bit. So what I want to do is I'm going to show you an example, and I'm going to kind of walk you through the process of it and show you why we do it. So this is the example that's in the folder. Real simple, real straightforward. Okay, what's happened is I've gone ahead and I've randomly selected some teens from age 15 to 17. I found out that 57% of the 248 boys had posted an online profile. I had found out that 70% of the 256 girls had posted an online profile. So what I want to do is the following. I want to see the difference between the two. I want to look and see what would the sampling distribution of these two samples, of these two groups, look like if I kind of pulled them all together. So the way we do this is we got to check everything like we did before, but twice. So what we're going to have to do is we're going to have to check the shape for the boys. We're going to have to check the shape for the girls. We're going to have to check the center for the boys. We're going to have to check and calculate the center for the girls. We're going to have to calculate the spread for the boys. We're going to have to calculate the spread for the girls. And the way we do that is everything here is this 2 times. So it's once for boys, once for girls. Once I do that, I can then use my rules to put things together and do some calculations. So looking at this problem, when this thing comes to my center is always the random check. Do I meet the random check here? What do you think? Looking at this, do I meet the random check? Was this thing done randomly?
Yeah, because it says among randomly selected.
It says randomly selected at the top. That's all we got to work with, is just that phrase. So it's randomly selected. So what that means is the following. I can do the following. Since they're both randomly selected, they're called unbiased estimators. What they mean is if I kept doing this process, 248 boys, 256 girls, and I kept doing this process over and over and over and over again, I would find out the following. I'm going to make my best guess. I'm going to say the average of all of those p hat for boys is going to be that 57% I just came up with. I'm just going to go on that because I don't know any better. We don't really know the answer, so we're going to use our sample as our jumping off point. For girls, I'm going to use the 70% that I got. That's my best guess. Now, sometimes in a problem, you're going to see a sentence that says, it is known that 72% of girls post online profiles and 68% of boys post online profiles. So it'll have something like that perhaps in the problem. Those are going to be the, if it says like, we believe this or we know this, we're going to use that. If we're not given that, we got to use the sample. All we have in the world of statistics, if we don't know the real answer, all we can go off of is the sample. So I have two centers now. The center for boys is 57%. The center for girls is 70%. So if I were to ask you, what's the difference between boys minus girls? What would be the difference between the boys and the girls?
Negative 0.13.
Yep, negative 13, negative 0.13, because 57% minus 70% gives me negative 13%. So what I'm saying is that when I put these guys together, I would expect it to be centered at negative 13. I would expect there to be 13% more girls than boys with online profiles. That, given this sample, that's all I got. That's where I'm going to jump off. I'm going to think the center of this is at 13. So that's our center. So any questions on center? Okay, we're going to talk about spread next. Spread is the 10N check. So what I want to do is I want to think about the 10N check. So I'm going to think about 10N for the boys. I'm going to think about 10N for the girls. So what's my sample size for the boys? From the problem, what does it say? Our sample size?
248.
248. So I'm going to do 10 times 248, which is going to give me 2,480. I'm talking 15 to 17-year-old boys. Do you think it's safe to assume there are more than 2,480 15 to 17-year-old boys?
Yeah.
Yeah, online, I would assume yes. It's pretty safe. And I'm going to do the same thing for girls. So I'm going to do 10 times the 256. I'm going to get 2,560. So I think it's safe to assume there are more than 2,560 girls. So basically what I'm going to assume is the following. I'm going to make those assumptions. I'm going to say, hey, it's safe to assume there's more of those boys than 2,480. There's more than 2,560 girls. And now what I'm allowed to do is the following. I can calculate two different standard deviations. What I can do is I can go and use this formula sheet and take the 57%, which is the number I had for boys. Again, it's this formula right here, and it's on your formula sheet, and it's like a plug and chug kind of thing. You take your numbers, you plug them in, you get your answer. So 57% of boys have an online profile, 1 minus 0.57 over 248. This one's going to be 70% for girls, 1 minus 0.70 over 256 for girls. And what I get is I get standard deviations. So what it says is the boys are going to be centered at 57% with a standard deviation of about 3, a little more than 3. The girls are going to be centered at 70% with a standard deviation a little bit less than 3. So that was, again, think of the Reese's Pieces. If I just did boys, it was kind of like what we did with the Reese's Pieces. But now what I'm saying is I'm going to do it a second time. So now this is another new thing. How did we combine standard deviations? If I had told you the following, the standard deviation of boys was 4, the standard deviation of girls was 3. How do we get the standard deviation of boys plus girls? Is it 4 plus 3? Nope, can't do it that way. Remember, standard deviation always makes me work. So what I need to do for this is I need to turn both of them into variances. So the first thing I needed to do was get the boys as variances. I needed to get the girls as variances. I needed to always add them together and then take the square root to get the standard deviation. So what I'm telling you is there's a formula that we're going to use when we combine the two. So what I want to do now is I want to figure out the difference between these two standard deviations. And on the formula sheet, the way you figure out the difference is this. It's a big old ugly formula. I'm going to take my proportion for boys, 1 minus my proportion for boys. I'm going to put it over my sample size for boys. So I'm going to take this first one. I'm going to add it to the same number for girls. The way I'm going to do it is I'm going to take these two, because just so you know, this thing underneath the radical that we learned with Reese's Pieces, under the radical, that's actually the variance of that sampling distribution. We square rooted to get back to the standard deviation. So this thing under here is actually a variance. This is how we're going to find a combined standard deviation. We need to use this. And again, this is on your formula sheet. It is on your formula sheet. So we're going to plug in chug. So what's going to happen is when I go to plug all of these in to find the difference, I'm going to plug in all the numbers down here, and I'm going to get a new standard deviation of 0.0425. So this is literally substitution and simplification using the calculator. So I'm going to use this formula to get my standard deviation. So like Rafsa said earlier, my center was negative 0.13. My standard deviation was 0.0425. So now I'm getting a new standard deviation, a new mean, and that's what I'm going to use. That's probably the trickiest part of the whole process, is that new idea of a standard deviation. But here's the thing. We are literally going to use this formula right here every single time we do an inference test, an inference confidence interval. We're going to use this formula. You're going to get used to this formula to the point where you're not even going to need to look at the formula sheet to use this. I mean, we use it for every single problem we will do. If we have two samples, we are always going to use this. Even when we get the means, it's still going to be the same general idea. So I got about 7 minutes left. Last thing I wanted to talk about was shape. In terms of the shape for the boys, I got to make sure that when I took this sample that I could be sure that I'd had 10 or more boys with an online profile, 10 or more boys without an online profile. What says 57% of these 248 boys have an online profile. So that means that 248 times 0.57, about a little over 141 have an online profile. That's greater than 10. I do the same for failures. 248 times the complement to it, 1 minus 0.57, says 106.64 boys do not have an online profile. Both of those numbers exceed 10. I know my shape of my distribution is normal. So what I'm saying is this is for boys down here. Boys are normally distributed with a mean of 57%, a standard deviation of 3.1%. Same process for girls. When I do the math, I find out 179 girls exceeds 10, 76.8 do not have profiles that exceeds 10. So now for my girls, I have a distribution. And what we talk about putting them together is using those rules we learned about combining means and combining standard deviations. Easiest one rule to know is this. If both of my distributions are approximately normal, like they are, when I combine two together, whether I add them or subtract them, the shape is going to remain approximately normal. To figure out the new mean, it's like we talked about at the beginning when I was talking with Rafsa about it, it's negative 0.13. That's the new center. And like I mentioned with that standard deviation, it's going to be 0.0425. So what I've done is I've taken two distributions, I've subtracted them from each other, and I've ended up with the following distribution. This distribution is boys minus girls. So if I were to do this over and over and over and over again, I would expect the difference of boys and girls to be centered at negative 13% with about a 4.25 standard deviation. So in other words, this is what I'd expect. That right there. This is my distribution, my sampling distribution of boys minus girls. Centered at 13%. I'm going to go ahead and add 4.25 each time. I'm going to go ahead and subtract 4.25 each time. I would expect with 99.7% confidence that my difference should fall somewhere between negative 0.225% and negative 0.25 3/4%. So looking at this, based on this distribution, would you be surprised if I ended up with more boys with online profiles than girls? Would you be surprised if I ended up with more boys with online profiles than girls? Because this is the difference, boys minus girls. What would it mean if boys minus girl, if boys had more online presence? What would that mean for the difference between the two? If boys had more online than girls? What kind of number?
Wouldn't it be a positive number?
That'd be a
more
positive
boys?
number. Do we see positive numbers on this curve at all?
No.
No, it goes from negative 25% to negative 2%. Boys minus girls is way over here. So what that would say is that I would not expect to find a sample where the boys exceeded the girls, or if I did, I would be incredibly surprised at that. That something might be going on there that I might want to look into. Either there's two ways to look at it. The first way is, hey, something's going on at this school that isn't going on at another school. If I was pulling this from, like, say, on high school, or let's say you pull a sample and you ended up here where the boys were greater than the girls online. What I would do is maybe come back and say, hey, you know something, you know that claim you're making that girls are more online than boys? I don't necessarily buy it because I did it. I ended up here. I shouldn't have ended up here given what you told me. So the idea of a sampling distribution is when we're taking two of them together, the big thing to take away is this. To figure out the difference, it is literally just subtracting the two proportions from each other. That's all it is. When we're figuring out the standard deviation, we have to use this rule. And the final piece is the shape says the following. If one is normal to start with and the second one is normal to start with, at the end, their difference is normal as well, which is good. So if for some reason, let's say this guy was skewed and this guy was approximately normal, what you'd have to tell me is, hey, Mr. Oliver, I can't figure out the shape because they both need to be normal in order for me to tell you the shape. So that's kind of like what we did last time. This example is there in the folder on Schoology, the virtual day folder. There's a practice problem there that looks just like this, that you can work your way through, that I've given you the answer key to as well. So what I'd recommend you do if you'd like to practice this before next class, just try that problem, look at the answer. I'm going to move the video over into the folder for that question so that you can kind of take a look at me explaining it. So, but that's what I got for today. On Wednesday, when I see you again, what we will do is we will dive into means. We will go to means and we'll kind of follow the same process for means. So let me stop the recording.